All right, we're going to finish our probability of discrete events. So the discrete events are a finite, countable number of possibilities. So the number of cars that drivers that are wearing their seatbelt at the stoplight, that's going to be 1 or 2 or 3 or 4, not 3.5. Okay, not 3.467. Okay, so a finite, countable, discrete possibility of events. Now, we need to remember the difference between the two key types of discrete probability: geometric and binomial. So let's remember that. Geometric probabilities are going until a success happens. That's the catch. So what's the probability that you don't find somebody wearing a seatbelt until the third car? Okay? Or whatever. So things that can happen with geometric is they will tell you, just like I just did a moment ago, until the third car, the exact place that first success will happen. So usually we just say, okay, failure, and that first one's a failure, and the second one's a failure, and the third one is the success. Okay? And so then we multiply those three events together. Now, if we were to use our calculator with that, if it's exact place of a particular success, then we could do geometric PDF. So we either can do what I just showed you with writing out the three events and multiplying those together, or we do that geometric CDF where we go, it's under distributions because geometric is a type of distribution. And we go on up there. I go to the bottom. I usually go up. So here's PDF, geometric PDF. That's going to tell me the exact place of the first success. So I say, okay, there's 85% of people wearing their seatbelt, and I want that success to occur in the third spot for the first time. Okay, and so on. And that's how you would do that. All right, then that would put 2 failures and then a success. Now, let's take a look at what happens if we are accumulating this. What happens if I say, hey, I want what's the probability that the person wearing a seatbelt is on or before the third place? On or before. So that could be the third place, or the second place, or the first place. So technically, I could add together a success in the second place and a success in the first place. I could add together these three situations, or I could allow accumulation, adding up all of those successes. So I want the success to occur in the first place, or in the second place, the first success, or in the third place. You could calculate that with geometric PDF. So, the slow way of doing this, of course, is going to be, let's see here, let's quit this here. The slow way, is going to be when you're doing your 0.85. So that's the first success. Then we want to add to that failure and then success. So here's my failure and success on the second time. Or failure, failure, success. So that's your 0.15 times your 0.15. So failure and success. Okay, so that's kind of a lot of work, especially if you get a whole bunch of stuff happening. See, here's one event, or the second event, or the third event. Or PDF, or accumulate those three items. So that would look, again, under second vars for second distribution. I want to do a geometric distribution, accumulate. So I'm going to come down here and I'm going to accumulate, and I want the probability proportion of people wearing their seatbelt is 0.85, and I want the success to occur on or before the third car. So that's going to total up those three pieces together in one fell swoop. Okay? All right. Next, what if we want a success after a certain place? What if I want the success to occur not in the first three? Anything else, just as long as the first three are not a success. You could do that a couple of ways. You could say, okay, well then we got 3 failures for sure. Or you could do 1 minus the 3 successes on the lower part will give you everything after that. And we'll talk more about that here in a minute. Now, one last idea. If you were to turn this discrete, finite, success on the third spot, success on the fourth spot, or whatever, into continuous, then we would have this. How many items or how many cars do you expect to look at until you find a person wearing their seatbelt? How many cars do you expect? Expected value is the mean. How many cars do you expect until a success? So on average. Now this is on the formula chart. So let's look down here. This is what your formula chart looks like. And see, and here we are on our geometric. So we have the failures and then the success. Okay, well, here's the mean. How many do you expect to go? So if it was our car situation, then I would say, oh, how many cars do I think I'm going to have to look at until I find the first person wearing a seatbelt? That's 1 divided by the probability, so 0.85. So on average, in the long run, if we did this many days in a row or on many randomly selected days, I'm going to have to look about at 1.18 cars on average to find the first person wearing a seatbelt. Okay. And with what standard deviation? How varied is that going to be? So you just fill in that formula there. All right. That is the geometric. So now let's take a look at the binomial. All right, so here we go with the binomial. What is the binomial? How is that different? Okay, so with the binomial, the difference is we are not going until a first success. We are seeing, hey, bam, out of a set number of trials, say out of the first 10 cars at the intersection, out of a set number of trials, so N is known. Then, what's the probability you have? You could say exactly 5 of them there's 5 of the car's drivers wearing their seat belts. Okay? So that is exact number of successes out of a set number of trials, not going until a success. So let's take a look at this formula down here for that. So for our binomial, do you remember for our showing of the work and everything, we have to do this writing of this formula. So here we have the probability that we get exactly, let's say we're going to do that 8 successes out of the 10. 8 are wearing their seatbelts. So there's 8. All right, now this part right here tells me all the combinations. I cannot just go, 0.85, and I want 8 of those to be wearing their seatbelt. So I cannot, again, let me get myself some room here. I cannot just go, hey, I want exactly 8 successes. Okay, well, wearing their seatbelt is 0.85, and I want 8 of those, which would mean that not wearing their seatbelt, there are 2 of those. out of 10, out of 10 drivers that you look at. Okay. The reason is because you have many different combinations. These 8 successes can be sprinkled in any place amongst those first 10 cars. So we have to account for all the different combinations that can happen. That is where this comes into play. Out of 10, choose 8 successes. Don't put a fraction line there. This is good. This is a very complicated factorial computation of how to get all the different combinations, okay? So, this is the work that you show, but yet then you should just go to your calculator to do the computing. So, because you do not want to calculate these combinations by hand. So when we go to our calculator, calculating something such as this will look this way. So we're going to go to our distribution. It's a binomial distribution. So second vars, and I'm going to go up, and I'm doing binomial PDF because it's exact, a particular number of successes. So here I have that, and number of trials. See, this did not show up on the geometric. So out of 10 bars I'm going to look at, and the probability of wearing their seatbelt, 85%, 0.85%. Okay, exactly how many successes do you want? 8. So I want exactly 8. And so then that is how I do that value. Now, if you did not have a calculator that has the menu, you end up typing it in just like it has here, binomial PDF 10. So out of 10 items, comma, 0.85 is the successes, and then comma, 8 successes. All right? So that is how you would work exact number of successes. All right. But what if it wants an accumulation? What if I want less than or more than? What if I want at least or at most? Okay, so let's take a look at that. Let's actually, I did that wrong. Let's say less than or at most. If I want less than or at most, so again, let's go with our 10. Let's say I want to find the probability that x is at most 8. That is less than or equal to 8. Okay, so then when you show your work, the most you should ever have to show is 2 parts of the sequence. So we're going to do this for 10 with 0 successes. And then I have 0 successes. And then and then that would make 10 failures. You remember this? Plus, dot, 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 plus, and then the top part of the sequence. 10 with 8 successes because I want 8. If it had said less than 8, then I'd be putting 7 here. Okay? And then 0.85, I want 8 of those, and 0.15, 2. So now, calculator-wise, this is going to be an accumulation. And our calculator accumulates only below. So that's what we want here. So that's good. I want from 0 up to and including 8. So I'm going to, second vars, I'm going to come on up here, and I'm going to binomial CDF so I can accumulate up to and including 8. So out of the 10, 85% are wearing their seatbelt. I want up to and including 8. If I had said less than 8, I'd be putting a 7 right there because I want 7 and below. All right, so here is then our probability. 45.57% chance that at most 8 will be wearing their seatbelt. All right, and the one final component is what if I want the top part? What if I want more than 8 or at least 8? And if you remember correctly, that is tricky because the calculator will not compute for you top part. If I want, so let me show you and remind you this here. If I want the probability that x is going to be, let's say, greater than or equal to 8, okay? So then that would look, I would show the work, the first in the sequence up to the last in the sequence. So I want 10, choose 8 successes, 8 successes, and that would be 2 failures plus dot 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 plus 10 success, 10, because I'm going all the way up to the top. All right, and so then I have 10 successes and 0 failures. Okay, and you can write that in there. But calculator-wise, here's the issue. So if we think about 0 successes, 1 success, 2 success, so on and so forth, up to 7 successes, 8, 9, and 10. If you remember, the calculator does not accumulate from a midpoint up. So I'm going to always circle what I want, and I want 8, 9, or 10 successes. But that calculator is limited and won't give me 8, 9, or 10 successes. It'll only give me this bottom part. But that's the part I don't want. So there you go. What are we doing? We're going to take everything 100% and take away this part that the calculator will give us. So 1 minus that bottom part will give us the top part. So the way that will look in our calculator is like this. We're going to say, okay, 1 minus, then I'm going to do that binomial. Let's see here. I don't think I did that right there. There we go. And I want to take off the bottom part. Okay, so here I go. Now, do you remember what part am I taking off? Okay, let's look back. What part am I taking off? I am taking off 7 and below. Don't you take off all 8. You want 8, so take off 7 and below. So I put a 7 right here because that's the part I'm taking off. So see, look, 1 minus the binomial accumulation of 7 and below, and that then is how I get the top part, at least 8, 9, or 10 successes. All right, that's about as tough as it gets. Let's remember one last little thing. If we want to turn this into expected values. So, hey, out of 10 cars at the intersection, how many do you expect to be wearing their seatbelt on average? Well, that's their formula. And with what standard deviation? Okay, again, that is this. So out of 10, this is going to be the mean, and this is going to be the standard deviation. So that will tell me the number of cars on average and with what variability I expect. Okay, I think that pretty much takes us, look, that was all to the end of that. You're going to then have your geometric practice here, and then your binomial practice, and combined together, telling the difference between those. All right, so that is, again, practice, 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 the only way to go. I hope that this thinking map here is a good visual representation of all the ways that you're going to handle these problems, okay? Good luck to you on this.